circle is back.
Our first is going to be what happens if we, kind of like we saw yesterday, what happens if we, say, create two angles and the vertex is on the interior of a circle. And rather than analyze the angle measure, we're going to look at actually segment lengths inside of here. So if I have, say, a circle, and I'm going to draw, say, here's one segment, and here's another. I'm going to label these things. I'm going to call this, say, A, B, X, and Y. Just pick 4 letters. Those are the ones I like the best. A is supposed to be in this section. B is the length of this segment. X is the length of this segment, and Y is the length of the segment. The segments of chords theorem says the following. It says that for two chords within the same circle that intersect for two chords within the same circle that intersect. So I have that situation. I have two chords, they're in the same circle, and they're clearly intersecting. The following is true. The product of the parts of each chord are equal. Product meaning multiply. So if I multiply the length of each part of the chord, those two things have to be equal for either chord. Or creating a formula out of this, from this circle, these two chords intersect, therefore the product of each of the parts is equal. Or A times B is equal to X times Y. Would be a formula that we could come up with from via this theorem. We can analyze the proof of this at a later time. I want to look at a few concrete examples of this, and then maybe we come back to actually proving why this is true. Yeah, this is for two chords that are intersect two chords. Or notice this is very similar to our angle whose vertex is on the interior of a circle. Okay? We're looking at the chord length. So if I want to find the value of, say, a missing variable here, in this circle I have two chords that are intersecting on the interior of a circle. So therefore, if I were to multiply each of the parts together, those things should be equal. Or in this case, 6 times 4 better be the same as 3 times x. 24 is 3x. X better be of length 8. Or this segment better be 8. And hopefully that looks, if this picture is drawing even close to scale, that actually looks about right. X looks clearly just a little bit bigger than 6 and clearly bigger than either 3 or 4. In our second example here, so x plus 10 is meant to go with this segment. So we could say that x plus 1 times x plus 10 better be x plus 13 times x. Two quantities multiply together, you need to distribute, or even better yet, since we're here, we'll double distribute, aka FOIL this thing. So x, now we get x squared plus 1x plus 10x plus 10 is equal to x squared plus 13x. Note that we have x squared on each side. However, if I subtract x squared from each side, oh, wow, we don't have a quadratic anymore. 11x plus 10 is 13x's. Subtract 11x, divide by 2. 1x plus 10x is 11x. 1x and 10x is 11x's. 1 times 10 is 10. Equals 2x. Subtract 11x from both sides. X is 5. It's a bad word, don't use it. Our other possibility, so like we saw yesterday, folks, like we saw yesterday, if two lines or two segments are going to intersect, they either are going to intersect inside the circle or they'll intersect outside the circle. Those are only two choices. Our first choice we've already looked at, what if they intersect inside. So now we're going to look at, well, what happens if they intersect outside. And there's really 3 ways to create segments from what we've been given. If I'm going to have 2 segments intersect, I can intersect in relation to this circle. I could have the following. You could have, say, how about 2 secants? There's an example of 2 secants that intersect outside of the circle. 2 secants that intersect outside my circle. Notice they intersect the circle twice. They intersected, and I can look at, say, I can compare some parts. I can compare, say, the relative size of the parts of these triangles. You could have, say, we have a tangent and a secant. So you could have 2 secants. You could have 1 tangent, 1 secant. And what's our only other choice, really? You could have 2 tangents. You could have 2 tangents. Those are really your only 3 choices. If we're gonna have segments that intersect outside of our circle, we have one of these 3 possibilities. Now, we've actually already discussed segment relationships in regard to 2 tangents. If 2 lines intersect such that they're both tangent to the same circle, what do we know about the lengths of this segment and the lengths of that segment? They are congruent. We discussed that, I believe, in the first section of the chapters, either section 1 or section 2. We discussed the lengths of 2 tangents that intersect outside a circle. What we're going to explore on the backside of this, our second theorem is going to talk about how do we talk about relative lengths in these 2 cases, where what if in fact they're secants, or at least one of them is. And that's our final theorem for today, which is segments of secants or tangents. It says the following. It says for two secants But I want to say secants. I'm going to go, yeah, sure. Two secants that intersect outside of a given circle. The product of the secant segment in the part, or the external part. Of the secant segment. Are equal. Let's get a drawing and get a formula. So if I have two secants, so that's two secants. And I'll label this point, you can both use it as like E, I want to say right there. A, B, C, and D. For two secants that intersect outside. So I have two secants, they're going through the circle, and they're intersecting outside my circle. The following is true. The product of the secant segment, or E to A, and the external part of the secant segment. So for a secant segment EA, what would be the external part of this? External being outside.
Oh, wait, sorry.
EB is the external part of this. EB is these two things are equal in both secant segments. So EA and EB, if I multiply them, is going to be the same as the whole and the external part. So if I want to find the missing, sorry. This theorem not only applies to secant segments, it applies to tangents as well. And if we're talking about a tangent, we'll do a little illustration. Let's say I have a tangent instead. It's a very, very similar drawing in that I have two segments that are intersecting my circle, and they actually intersect outside the circle. I claim that the theorem we just wrote down applies to this drawing as well, even if I don't have two secants. If I have a tangent and a secant, and in fact, I also claim that it applies to two tangents as well. But we'll talk about that case a little bit. If I have a tangent, my theorem says, well, for any two lines that intersect a circle outside of the interior on the exterior of the circle, then I want to take the whole length and multiply it by the external part, and that should be equal to the other segment if I take the whole length and multiply it to the external part. So in this case, one side of the equation I could come up with would be like the length of YW times its external part would be one side of my equation. What's the whole length of the other segment I'm going to analyze? What would be the whole length of the other segment? xy. What's the external part of this tangent segment? Is there anything that's on the interior of the circle, if this is a tangent segment? Is there anything on the inside? No. So then what's on the outside? The whole thing, the same thing. So xy again. Xy is just squared in this case. So for tangent, the book I think has a second theorem, as this is a separate theorem. They're really the same thing. This is just a special case where I have the whole length and the outside are actually the same. For a tangent segment, the whole length and the exterior are actually exactly the same. So I think the book would write this as yw times yz equals xy squared. I believe it would say it as a second theorem for it. I don't like the idea of memorizing a second theorem when we can just apply one to both cases. Anyone see what would happen, like why I claim that this theorem actually applies to if you had two tangents? Like using that line of thinking, why would this theorem apply? Why is our previously held conception that if I had two tangent segments that they're got to be congruent? Anyone see why that would have to be? How this theorem would apply to it? Like what would we do if I made both of these tangents? I would just take like xy squared should be equal to whatever this is squared. So if I square root both sides, I get this piece is equal to this piece, or whatever. But the theorem holds for our already conception of that if there are two tangents intersecting outside, they should be the same. The theorem actually fits that. That's a good thing. It's a very good thing. Anyways, so this idea of applying it to tangent, let's look at a couple examples. Find the missing length. So I have two lines that are intersecting outside of my circle. So I want to use my theorem to set up an equation. I know that since they're intersecting on the outside, I know that the whole length times the outside piece, the exterior piece, better be equal to, of one of these segments, better equal to the whole length times the exterior piece. Well, if it's tangent, then they're both the same length. We're gonna find that, especially for this section, those factoring skills that we applied, that we worked on before, are going to come in very handy. Because we're going to see a lot of either squaring for a tangent piece, or in this case, the whole length of the segment is this variable plus constant. We're going to end up with some quadratics quite a bit. So if I distribute here, I'm going to get what, 4x plus 20, 4x squared plus 20x is 9x squared. Boy, I would have solved this. Sure. We can do that. And that's going to leave us with, I'm going to we'll end up with the same answer. We can do that. Sure, let's do that. I like to actually, so we won't get a number. So we get what? 2x 20x equals 5x squared. Sure, we can divide by 5 if you want. You get 4x is x squared. At this point, if we divided by x, which some of you are kind of clamoring for, if we divide by x, we may lose a solution. We may lose a possible solution. We don't really want to do that. What we could do, another idea might be to subtract 4x from both sides. You can get x squared minus 4x is 0. and finish solving this by factor. Oh, I told you you're going to probably want that. Well, this is an easy factoring one because there's something in common here. What's in common? X. So I can say X, and what's left over if I take out an X from each of these? If I take out an X from X squared, there's an X left over. If I take out an X from -4, there's a -4 left over. So algebraically, my two possible answers are what? X is 0 or X is 4. Which one fits this problem?
4.
The 4 does. Now you may get mad at me and say, well, if I just divided by X, I would have got that answer anyways.
Yeah.
If this was, if I were to play maybe, I don't know, I feel like you could probably make, rearrange this diagram such that we could make the 0 actually the one that works and not the 4. I feel like if I mess around with the maybe negative signs or the links here, it's possible that we don't want to just discount all these possible solutions. We may at the end just throw them away anyways, but we don't want to lose them is the key. If you start dividing out the variables, it's like a good chance we're just not going to even see the solution, which may or may not be the argument. X is 0 and then not being 0. Okay. Okay, I'm going to delete this, give myself a little more room. In our second one, let's get this second guy set up and we'll work through the algebra together. So I have, let's see, in my first segment here, these are two lines that are intersecting outside of the circle. So I know that external part times whole should be equal to external part times whole, or x times x plus 8. The whole segment is x plus 8. And that should be equal to my external segment, x plus 1, times the whole segment. What's x plus 1 plus 5?
X plus 6.
These two things should be equal. Now I think, by looking at by inspection here, I think if you FOIL both sides, we'll end up with something where I think we won't have to do factoring over this one. So I think our x squareds we'll be able to subtract out just by looking ahead. We get x squared plus 8x, and that's equal to x squared plus 1x plus 6x plus 6. We got x squareds on both sides. 8x is 7x plus 6. Subtract the 7x, and we should get x. X is 6 in this case. Well, finding these segments, I guarantee you at various points you're going to have to factor. So don't discount that. If you're in a spot, you may have to use solve by factor. Grouping everything on one side, set the equation equal to 0, and now try to factor into GCF, or maybe box and diamond like we practiced. It can happen. I have two practice problems that I'd like you to set up and try to solve on your own here before I throw up the homework assignment. Yeah, you probably already have it. I want you to work on these so I can just keep them. All right, finishing these guys off. Most of you already got this. Let's see. External part times the whole segment. X plus 4 is equal to external part times the whole segment. 5 plus 3 is 8. So 4x plus 16 is equal to 40. 4x is 24. X is 6. Hopefully we get x is 6 for the first one. Secondly, let's see, we have external part times whole segment, which is 10, is equal to external part times the whole segment. For a tangent, they're the same. So 60 equals x squared. Square root of each side, we get x. Technically, we get plus or minus, but we can't have a negative length, so we'll throw that out. And then root 60 is 2 roots of 15. If you need a reminder for simplifying radicals, you could go back to the algebra review from chapter 7. I believe I still have that video posted on our website that you could check out for a quick algebra review of that.